Hi, my name is Emma Brunskill, and I'm an assistant professor of computer science at Stanford University. And I'm thrilled to be here today to talk to you about some of the work that I do with a number of my amazing students and collaborators. So, I think many of us in our professional and personal lives face the question of how do we make sequences of decisions under uncertainty? For example, a doctor might ask, will putting this patient on a ventilator maximize their chance of long term survival? Or in the case of education, a teacher or someone designing an intelligent tutoring system might ask, how do we adaptively teach algebra in order to increase the number of students that pass the course? Now, this question of how to make sequences of decisions under uncertainty when we don't know in advance the outcomes of those decisions, is often referred to as reinforcement learning. And the idea of how we do this, how humans and artificial agents can quickly learn to make good, robust decisions, is really a central question in artificial intelligence. In addition, I care about this question a lot, both for its fundamental value, but also because I think that answering it is going to be core to advancing artificial intelligence for human benefit. And so, really, the majority of work that I do together with my wonderful students, collaborators, and postdocs can really be summarized by a deceptively simple question, which is how can a machine learner learn from limited samples to robustly make good decisions? I think it's helpful to talk about briefly the way in which we approach this problem, because in my lab, I think about doing this both from the perspective of applications, predominantly to education, but also some to healthcare, as well as developing generic algorithms that can be built upon as tools, and in addition to contributing theoretical results that help solidify our understanding of the foundations. So before I go into more of the details, I want to briefly say some of the main questions that come up when we try to think about learning from limited data. And I want to use this chance to contrast with perhaps some of the work you might have heard about in artificial intelligence and reinforcement learning. So last fall, there was a very impressive robotics result in which OpenAI showed that a robot could solve a Rubik's Cube. Now, inside of their paper, they note that the cumulative amount of experience the robot needed to solve that cube was approximately 13,000 years. If you would do a back of the envelope calculation, that probably means that the robot spent about 197 million attempts to learn how to do this. So you might think that if we need that amount of data or experience, that may not be realistic. But on the other hand, we know that there are enormous amounts of data now, including in healthcare, so perhaps we will have availability of this sort of data. But let me just illustrate an example where I think we might be able to use the types of techniques that I'm going to describe today. And that's for something like fitness. So you can imagine having some sort of fitness device that is providing you with nudges or interventions to help you reach your own health goals. Now, if we pick a fitness device that's been one of the most popular fitness devices ever, which is the Fitbit, and we look at how many of those have ever been sold, there's only ever been, since Fitbit started, approximately 90 million Fitbits sold. So if we compare to how much experience this robot hand is needing to learn the Rubik's Cube versus even in some of the best cases, how many people are using these fitness devices, we see a gap. And I think this really motivates the need for why we need algorithms and techniques that can learn from limited amounts of data, not just enormous amounts of data, in order to make good decisions. A second thing that we think about a lot in my lab is stems from some of the work that we've done in education, but has broader implications. So I just want to show you here briefly. This is one of the first tutoring systems that use reinforcement learning, and I'll define that more formally later. But it adaptively presented problems to students, and it did so in a way to try to maximize how quickly students could do problems. Now, if you contrast this to sort of what are maybe the objectives of an educational system, I put up here just one of the pages of the objectives of the Palo Alto school system, where my son goes. And you can see here that there's an enormous number of different objectives of that educational system, including things like performing at or above grade level, but also things like discovering passions and promoting equity. And so I think when we think about decision making under uncertainty, there's always implicitly an objective function that we're trying to maximize. And I think it's increasingly important to think about where those objective functions come from and how we can collaborate with domain experts and other people who are affected by these decisions in order to make sure that the objectives we're describing are really the ones we want. And I'll come back to that shortly. But I really want to turn my attention now to the thing that I want to focus on today for this talk, which is the third main focus of my lab, which is really about counterfactual decision making, or how we can leverage old data, existing data, to make decisions. And this is an area where I think is particularly relevant to healthcare and potential future healthcare applications. So, to illustrate what I mean by this, this is really thinking about the question of what if reasoning given past data. So, you can imagine that we have a sequence of patients or a sequence of individuals that are receiving particular orderings of treatment interventions. So, perhaps the first individual received medication and then also had a doctor's visit, and they had some outcome. Now, obviously, this is a simplified setting, but you could imagine that there is a series of people, all that are receiving some sorts of interventions from their doctor and who are experiencing some sort of outcomes as those are happening. And what we would love to do is to leverage that prior data and potentially variability in that data in how those decisions were made in order to make the best possible decisions for future patients. Now, inherently, this question is very hard because data is censored. So we can't see what it would have been like if we had taken the same individual and given them a different sequence of interventions. And so that's what I mean by censoring here. We're fundamentally dealing with a counterfactual of what would have happened under some alternative decision policy. And we need that in order to think about how we can use this old data to understand what might happen if we were to behave differently in the future and whether or not that would have better outcomes. Now, just another thing I want to highlight here is that as we start to think about the sequence of decisions that are made instead of just a single decision, this sort of complexity of the decisions made and when can start to be combinatorial. And so, for example, here I've only showed sort of a 2 time steps of decisions and a small number of different interventions we could take. But as you can imagine, as we start to think about longer sequences, we start to have sort of this combinatorial blow up of all the different sequences of interventions that we could do and how would we pick among these. And it's not going to be feasible to necessarily do a randomized control trial for each of these. And so I think a really important consideration when we start to think about not just single decisions under uncertainty, but sequences of decisions under uncertainty is how do we generalize? Can we get any sort of inferences from prior data that allow us to extrapolate or generalize in a safe and robust way to allow us to evaluate what might happen under different circumstances? So just to be a little bit more formal, the typical framework that I think about and many others think about in this setting is described by a Markov decision process, where we assume there's some sort of state or features or observations about, say, a current patient. And then we have a decision policy that maps from those states of the individual to what is the decision to make next. And then we also assume we have access to some outcome or reward or utility model that tells us about how good those decisions are. And those could be a combination of things like health outcomes for individuals, as well as the cost of some of those interventions. And given this, we often would like to be able to figure out how good is a particular policy. And the way we evaluate that is thinking about the expected discounted sum of future rewards that we would obtain by following that policy. Now, the key challenge in reinforcement learning, and in many real cases, is that we don't have an explicit model of what we call the dynamics model of how the world will change or how the patient's state might change under particular actions. So if we prescribe a certain drug, say an aspirin, will their headache always go away? Maybe, maybe not. We may not have perfect models to describe that. And so in reinforcement learning, we're often concerned with this question of how should we optimize decisions given access only to observational data or only observational or RCT data. But in particular, we're assuming that we have access to historical data where we have decisions that are made in those outcomes. And we would like to use that to figure out better ways to act in the future, if that might be possible. Maybe we can do even better than what we're already doing. Now, this question of this sort of counterfactual or batch or offline reinforcement learning is an important one in many different fields. Many of you may be already doing work on this. I know that a number of the other speakers are also thinking about this. And I think in general, we're seeing increasing interest, at least in the artificial intelligence community, in thinking about these sort of causal inference and machine learning and counterfactual questions. But the majority of this work, and there's also been a lot of work in epidemiology and statistics and econometrics, the vast majority of this work has focused on when there is a single binary decision. So we want to make a single decision, say, of prescribing some medication or an injection. But I'm really interested in the case of when we make sequences of decisions. And I think that there's a huge importance of sequential decision making because many, many cases in healthcare and others involve not just making isolated decisions, but decisions that we hope will impact the state of the system, or the state of the patient, or the state of the student. So this is a figure I really like a lot from a paper from my colleagues Finale Dashi-Velez's lab and David Sontag's lab, which is thinking about reinforcement learning in healthcare settings. And I think this illustrates the importance of sequential decisions, where we think about making a sequence of decisions and hoping to maximize long-term outcomes. Things around whether or not we do mechanical ventilation or sedation or vasopressors, where we expect and hope often that these interventions are leading us to better and better outcome states for the patient. Now, one of the big challenges when we do this is that if we want to think about acting differently in the future than the way we have acted in the past, then we expect that the outcomes and even the states we reach will be different than what we've seen in the past. And so that induces this big challenge in that in a lot of machine learning, we tend to assume the independent and identically distributed assumption, meaning that we assume that the prior data and the future data are going to come from the same distribution. But the problem with doing this sort of off-policy or counterfactual reinforcement learning is that will inherently be false, because we're hoping to think about what-ifs or counterfactuals that are different than the way we've behaved in the past. So some of the central questions for batch reinforcement learning are off-policy evaluation, where we are given the particular new decision policy, and we'd like to estimate how good it is. What would it be, its average outcome or its expected discounted sum of rewards? We also often are interested in quantifying our uncertainty over those estimates. Can we have upper and lower confidence bounds on its performance? And that can be very important for us to decide whether or not we have a new decision policy that is worth deploying in the future. But a second really important question, and indeed one of the reasons we are doing off-policy evaluation, is that we want to do off-policy optimization, meaning that we want to use this data and we don't just want to evaluate how well something else might do, but we want to find the best possible thing we should do in the future. And this is the question that I want to focus on today. So while we've done a lot of work on the previous one, feel free to ask me in the live sessions about that. But for today, I'm going to focus on off-policy optimization. And in particular, in my lab and with collaborators, we've been thinking a lot about how do we work towards practical good off-policy optimization. And I'll tell you about 3 of the different projects that we're doing in this space. So to illustrate this, I want to give an example of diabetes insulin management. So imagine in this case that the decision policy that we're considering is how do we go from some sort of aspect of the physiological state of the individual, which could be their current blood glucose or other sorts of features that describes the patient's state, including meal consumption. And we want to use that to inform what the insulin dosage is. And imagine that we have as access historical data from previous individuals and dosages that were given and their outcomes over time. Now, one of the challenging things with this is we would like to maximize long-term outcomes for patients or for people with diabetes. And this objective function is complicated. We may be concerned with making sure their blood glucose is in the right range, but there may be different penalties according to whether or not their blood glucose is too high or too low. And in some cases, we may have hard constraints due to safety concerns over one of those 2 outcomes. So rather than just thinking in expectation, on average, how well are we managing their blood glucose, we may want to derive policies which have hard constraints on their performance under some of these different kind of multiple objectives. So this work was led by my former postdoc, Phil Thomas. And what we looked at here, along with some other wonderful collaborators, is thinking about doing this sort of off-policy optimization in a way that we could be guaranteed with high probability that in the future we wouldn't exhibit undesirable behavior. So undesirable behavior in this case could be things like having hypoglycemia, or it could be things about fairness. It could be ensuring that for men and women, we don't have significantly different outcomes in terms of how well the policy performs. And so we frame this as a constrained objective problem. And this is work that appeared in Science a few months ago. And we thought about this type of question of constraining the performance of machine learning systems for a couple different examples. But let me just tell you briefly about how this algorithm works. So it's quite a nice, simple approach. The idea is that imagine that you're in a case where you can sort of enumerate the number of different decision policies that you're interested in. Maybe there's a number of different ones people are curious about trying or considering trying for individuals. So what we propose in this case is that if you have this set of policies and it's finite, then we can use concentration inequalities, mathematical concentration inequalities, to compute bounds on the performance based on historical data and on whether or not we think these behavioral constraints on things like hypoglycemia, whether those would hold in the future with high probability. And then given the set of policies which we do think would satisfy our behavioral constraints, then we can pick the policy with the highest expected performance. Now, crucially, in some cases, if there's too little data, we may not be able to guarantee that any of the policies satisfies our desired constraints. And so in that case, our algorithm will explicitly return no solution. And we think this is important because we think that in order for people to trust artificial intelligence, we think that being able to have algorithms that sort of expose the limitations of either the algorithm or the data that they have access to can be very important in building trust so that we can know when things are not possible. So we looked at this for a diabetes insulin management case where we're looking at blood glucose control, and the action was the insulin dosage. And the constraint we put on there was hypoglycemia, though you could use other types of constraints. This was more for an illustration of the approach. And then we used a very accurate simulator that's been approved by the FDA to replace early stage animal trials. And what we found in this case is we're interested in the setting where you might have an individual, and that at the beginning we were that you might be exploring what is the best policy for that individual. And we want to use that data from some sort of default policy that's doing some amount of exploration of the different settings, and then understand when we could identify a policy that we're confident would do better and satisfy our desired constraint on hypoglycemia. And what you can see here is that at the beginning, if you use sort of a standard machine learning approach, it may be proposing new algorithms because it doesn't have this constraint, new policies, and it doesn't have this constraint, which can violate our desired constraint on hypoglycemia. But you can see in our case is that by about 100 days in, so 3 to 4 months, we can start to reliably be able to say, given the data we've seen so far, our algorithm is able to reliably output a policy that is satisfying the constraints. And in addition, it has this confidence. So we are able to sort of output this policy with fairly little data that is satisfying the constraints and going to work well. Now, as a quick note, I won't go into the details. You might be wondering, well, in many cases, we won't necessarily have a finite set of policies. We might have many different policies we're exploring. And for those of you familiar with policy gradient methods, those have been very influential recently. And we have also thought about how we would do this type of approach with an infinite set of policies for bandits, where we just have a single time-step decisions. And in this case, we were particularly interested in fairness constraints, looking at gender fairness or other subgroup fairness, and making algorithms that could satisfy those. So I just want to summarize that part by highlighting that this was a way for us to sort of think about these cases where we have a number of different sorts of objectives we care about, and in particular, some of those objectives might be constrained. And how can we find good policies under that circumstance? I now want to talk to you about a second thing we've been doing in terms of practical good off-policy optimization. So there's some standard assumptions that we often see for off-policy or counterfactual estimation and optimization. And one is known as overlap, and another is no confounding. So in overlap, we sort of think about this case where we have to take all the actions that the target policy would take. And I'm going to just illustrate this more in a second. So imagine that we're thinking about decisions a physician might make to treat someone with sepsis. So maybe for a particular state, we have some new decision policy that we want to evaluate, and it has the following probability distribution over antibiotics, mechanical ventilation, and vasopressors. So in this case, it would give a higher probability to giving mechanical ventilation, but it would have some probability of the other two, given the state representation. Now, imagine that we have a different policy that was used to collect the data. And for that policy, most of the time it provided antibiotics, sometimes mechanical ventilation, and less vasopressor. Now, this policy has overlap, meaning that it would also take all the actions with some probability that the policy we wish to evaluate would also take. But we could consider a modification of this, something like the following, where the particular behavior policy, the policy that was used to generate the data, never takes never selects vasopressors. So for example, in these settings, you might have the case that because of the state of the individual, that no physicians would ever prescribe vasopressors in this setting. And so that means that from the data that we have collected, we would have no way to evaluate how good it would be if we were to prescribe vasopressors in that state, because we would have never observed it in the observational data. Now, empirically, this can be subtle to know whether or not we have this overlap. If we don't have overlap, then we shouldn't trust some of our estimations, and I'll talk more about that in a second. But it can be subtle to know whether or not a new decision policy that we're curious about does actually have support in the data, because we often don't have explicit models for how decisions were made in the past. Our physicians don't normally give us a probability distribution over antibiotics or mechanical ventilation or vasopressors. And so this can be a hard task. And so sort of the main body of work that's thought about this before has simply assumed overlap. So typically, this is provided as, particularly for more theoretical work, including in some of our own, we typically often just assume overlap. We assume that whatever policy was used to generate the data and to make decisions in the past, that it covers all the types of actions and decisions that we are trying to evaluate for new policy. But I think in many settings, this is unlikely to be true, particularly because many real data sets don't include sort of complete random exploration. Something like healthcare, sepsis treatment, et cetera, we often won't have complete random exploration. And so there may be a lack of overlap. We may never try certain actions in certain states. And I want to just highlight why this can be a problem. So if we assume overlap when there's not, it can be a problem because we can end up computing a policy that thinks it's going to do well, but actually does poorly when it's deployed. So recently, together with my PhD student Yao Liu and several colleagues at Microsoft Research, we've been thinking about how do we do the best with what we've got. So if we have a data set that may not have complete overlap with all possible new decision policies, can we do something in a way that sort of allows us to do the best with the data we have? We sort of want to find if there are any better decision policies within the support of the behavior policy. And indeed, this sort of challenge of thinking about how well can we use the old data and how can we sort of reliably extrapolate from it is a common challenge that's attracted substantial interest in the last few years. But I just want to highlight briefly that unfortunately, some of these previous approaches are insufficient. So there's still more work to be done. So I'm not going to go through the details here, but we constructed several sort of illustrated small cases that illustrate why some of the recent approaches, including in deep reinforcement learning, are insufficient to tackle this problem where you may have lack of overlap. So we have several different cases where we proposed a new approach that works, but these prior ones can still fail to do well in that settings. And the idea here really is quite simple in certain ways, which is we're just going to constrain our policy class to sort of be within the sufficient support of the data that we have. And so we can change some of the standard operators that we often use to compute policies using standard machine learning, standard Markov decision process type assumptions. And we're just going to constrain some of those operators so that we can sort of stay within the support of the data. And we can prove that these sorts of approaches allow us to have nice guarantees with respect to the best optimal policy that does have support within the data. So I like this too because this is starting to get us away from sort of bounds relative to what is the optimal that's possible and really more focused on what are the bounds with respect to the best we could do given the data we have. So one of the things we observe in this case is that we can do substantially better and find substantially better solutions by taking this approach with the same data compared to some prior work, because we're sort of shaping and trying to find policies that we're confident will do better so that when we deploy them, and the y-axis here is showing the performance if we were to deploy them in the real world, we get good performance. So just to summarize here, I think that this idea is trying to move us towards saying if we want to go beyond one of the standard assumptions for a lot of the theoretical work, how do we sort of find better policies that are within the support of our data so we can sort of robustly identify new policies that we think are going to be good. And while we haven't looked at this yet in the healthcare for healthcare data, I think that would be really interesting to look at because I think healthcare data particularly have cases where because physicians are always trying their best, we don't expect to have full overlap with all possible policies. And we'd like to see if there's sort of some places we could further improve on top of physicians given the data available. So the final thing I just want to touch on very briefly is observational data and potential confounding. And this relates to one of the second standard assumptions when we think about off-policy and counterfactual estimation optimization. And that is no unobserved confounding, or often also referred to as ignorability. And in particular, this means that all the state variables used to inform the treatment decision are known or recorded in the data. Unfortunately, in observational data where we don't know the behavior policy, just like what I was mentioning before, sequential ignorability is often violated. So in the context of medicine, there may be features like visual observations or discussion that are informing very reasonably a physician's choice for making care decisions. But that those sorts of observations may not be recorded in electronic health records, or they may be recorded in places which are harder for sort of standard electronic medical records to be used to inform data, future policies. So maybe they're written in the notes, and maybe we can't always get good enough natural language processing to extract that information yet. Then maybe that'll change in the future. And even beyond this, even looking at the full records, it may be that some of the information that's really informing what are the treatments or actions that are taken are not being written down in the data that's available. And one of the problems with this is that if we lack that, if this assumption is violated, then our off-policy evaluation, and also if we do optimization, can be biased. Now, in general, this bias can be enormous. As soon as you start to have these confounding variables, you can be extremely large and have a huge influence in us trying to do things like estimation of how good another policy would do. And there's been some well-documented examples where there's disparities between, I can go into that later. I just want to highlight that this confounding problem can be very large. And there's some well-known documented cases for the one-time step where this can be a major problem. But one of the things is that in many cases, the amount of confounding may not be infinite. So sort of these confounding variables may not completely change the type of decisions that are made, but maybe they're sort of influencing. So maybe I'm more likely to prescribe aspirin if this particular unobserved confounder has some variable. And this has been a model that's been posited before. It's related to a model that has been used to think about the probability of lung cancer and smoking. And the idea in this case is to think about those unobserved confounders having a bounded influence in what treatments are chosen. So what we can see here in this case is that under some of these scenarios, we can start to get nice bounds for this setting. And I'm running out of time here, so I won't go through the details. But essentially, we can start to see some interesting cases where, despite this confounding, we may still be able to get tight bounds. So, with that, I'll wrap up. I wanted to share with you today these practical good off policy optimization methods and ideas that we've been looking at before. And I think in general, there's sort of huge potential to think about the intersection of reinforcement learning and healthcare. Thank you so much.